Hello. In the last lecture, we were discussing something about sequential definition for continuity, and we also discussed some questions on functional equations. Today also, we are going to continue with the same. And the series is all about continuous functions, and we are going to try covering it very exhaustively. And that's my target. Let us begin. Okay. So in the previous lecture, we already discussed about sequential definition. I'm just going to reiterate it so that it becomes a little bit nice to start with the background that we've already done. So initially we started that let J be a subset of R, where we actually said that intervals can be one of the profound example for a subset, but otherwise in general J is a subset of R. This is an important. Intervals can be one of the subset, yes, obviously. So let function be defined from J to R, be a function, and let's say A belongs to J. Okay, and understand that continuity is a local property, so we are going to define continuity at a point. Okay, so let A belongs to J. F is said to be continuous. F is said to be continuous at point A belongs to J if for every sequence xn in J with xn converging to A, we have fxn converging to f of A. So if this is the case, we say that f is continuous. So if xn be, and please remember for every sequence I'm saying, for every sequence xn and j, this must be the case that if xn converges to A, then fxn must converge to fa if f is continuous. So if f is continuous at A, then for every sequence xn and j with xn converging to A, we have fxn converging to f of A. We have to understand that xn must be in the domain of f. Okay, so this is something that one must note. Must be domain of f. And secondly, this limit f xn, this must be unique and uniquely assigned to fa. Let's say if I'm talking of xn converging to A, then this fxn must converge to f of A uniquely, and there should, if it is not the case, if the limit is not unique and in fact it is not equal to f of A, we'll say that function f is discontinuous at point A. So we have taken enough examples to show the same. So one of the examples that we took was fx is equals to 1 if x belongs to rational and 0 if x belongs to irrational. This we already took. This is a celebrated function called as the Dirichlet function, and we showed that this is discontinuous at each point. Why? Because we know, let's say for 0, if I want to play, so if I say is it continuous at 0, so I'll take two sequences. Let's say xn converges to 0. For every real number, there always exists a sequence of rational as well as irrational converging to that particular number. So if we are saying that 0 is a real number, we know that 0 is a real number. So uh, towards 0, you can always find a sequence of rational, sequence of irrational, or in general sequence of real converging to this particular number. Okay, that is 0. So for example, if we take only sequence of rational, let's say xn is equal to 1 upon n, what will happen? This converges to 0. If f is continuous, then f of 1 upon n must converge towards f of 0, and which indeed is the case, because f of 1 upon n will be simply equals to what? 1, and which is equals to f of 0, so that's fine, because we know that in any case, if you are taking a rational, then f1 upon n, this particular sequence will be a constant sequence. Are you getting my point? This is a constant sequence which is 1, 1, 1, 1, 1, 1, 1, 1, and this will converge towards 1, and which indeed is equals to f of 0. So certainly this is fine. But for 0, there may also be sequence like this, which does not converge at all. This also converges to 0, but fxn does not converge at all. It does leave f0. It does not converge at all. So clearly, function is not continuous at 0. Because why? For every sequence every sequence converging to 0, fxn must converge to f of 0. But here is a sequence which converges to 0, but fxn doesn't even converge, leave f0. Okay. So we could have taken another example. Let's say yn is equal to root 2 upon n. Certainly this belongs to irrational. And if I take fin, what it will be equals to? It will be equals to 0, because fin, according to the question, will be a constant 0 sequence. And this converges to 0, clearly does not converge to f of 0. So hence I can say that this function is discontinuous at 0. Similarly, what about rational numbers? If I take a rational number, let's say a belongs to rational, I can always find a sequence of rational converging to a and sequence of irrational, sequence of rational and sequence of irrational converging towards a. So for every sequence which converges to a, f of that particular sequence should be equals to f of a if function is continuous. If function is continuous, then for every sequence converging to a, we must have f of that particular sequence converging to f of a if function f is continuous. But that's not the case clearly. See, if I take fsn certainly will be equals to what? 0, 0, 0, 0, comma 0 dash dash dash. This is a 0 sequence, this converges to 0, and certainly this is not equals to f of a where a belongs to rational. So if a belongs to rational, uh, clearly this is not the case. I'm getting my point, because if a belongs to rational, then f of a will be what equals to what? F of a is equals to 1. And since a is rational, converging to a, you can always have sequence of irrational. So sequence of irrationals, uh, f of that particular sequence of irrational will give you 0, 0, 0, 0. So this converges to 0, does not converge to f of a, because f of a is simply equals to 1. So therefore, function is discontinuous at rational. Similarly, function is discontinuous at every irrational points at 0. So overall, I can say function is discontinuous on R. I hope this is clear. And I told you that there can be different ways of looking at it. And one of the way of looking at it is, if you want to construct a Dirichlet function, one can say limit k tends to infinity, limit n tends to infinity, cos of 2k n factorial pi x. So this is nothing but a Dirichlet function. So if you want to say how about this function, will it be a continuous function or not? Answer is this will be a discontinuous function on R. Why this is a discontinuous function of R? Because this is another way of writing a Dirichlet function only. How come? It's very easy to see. So for example, if x belongs to p upon q, so if x is p upon q, and if n is sufficiently large, so if n is tending to infinity, n is sufficiently large, so in the expansion of n, that is, if I expand n factorial, I can always find somewhere q, because this p and q are what? This p and q belongs to irrational integer sets only, except 0 here. So p upon q is this way. So I know somewhere you will have this q in the expansion of n factorial. And if you do so, and if you multiply by p upon q, so this cancels out q, so this becomes an integer, and n factorial pi x, if x belongs to rational, this will be an integral multiple of pi. And if you have an integral multiple of pi, cos will give you either -1 or +1. It will be either -1 or +1. And if you write cos to power 2k n factorial pi x, this will be equals to 1. So if it is equals to 1, so it implies that for all x belongs to rational, this particular entity will be equals to 1. And if x belongs to irrational, then n factorial pi x will lie between, cos n factorial, I should write rather. If x belongs to irrational, then this n factorial will survive, pi x will survive. So ultimately what I can write simply, I can simply write that cos n factorial pi x raised to power 2k will lie between 0 to 1 only. But when if I take k tends to infinity, now this will be a problem, because if this lies between 0 and 1, k tends to infinity, this will go towards 0. What will go towards 0? This will go towards 0. Cos 2k n factorial pi x. If I take k tends to infinity, because cos square anyway will lie between 0 and 1. So if I apply power k and k tending to infinity, so anything raised to power n, this turns 0 if a lies between 0 and 1. This is something that we have done in our sequences. So overall, this becomes 0 if x belongs to irrational. So overall, this implies that this is nothing but another bitter way or difficult way of saying that it is a Dirichlet function. Okay, so this is something that I just wanted to address, and we have done it in previous classes. But today we are going to study about something about functional equations, and let's see how things goes. Okay, so let's start with one of the very profound functional equation, which is called as a Cauchy's functional equation, and we'll do a few questions here today. And my task is to make shorter videos because I've heard from people that people don't listen to longer versions of these videos. So at least shorter, and I want to try and give as much as possible in these smaller sections and smaller videos so that you learn a lot and in a limited amount of time. Okay. So what is Cauchy's functional equation? This is something that I'm going to teach you today. And this is a way I want to start with functional equations. I'm going to do selected examples only today, and we are going to do uh, just give me a minute, a few more questions regards functional equations today. Okay, so now the question is that it's kind of additive homomorphism only. So just giving you an example, so let f r to r be continuous, let f r to r be continuous, which is also an additive isomorphism, which is isomorphism, additive isomorphism, that is fx plus y is equals to fx plus fy. Okay, for all xy belongs to R. Then one must understand that fx will be equals to what? It will be equals to some linear function which is lambda x, and here lambda is equal to f of 1. This is an important thing. This is called as the Cauchy's functional equation. This is called as the Cauchy's functional equation. Now let us start with saying that let's say n belongs to natural. Let us try to solve. But what's given that if functions show such kind of thing, that is f of x plus y is equal to fx plus fy, this is just an additive isomorphism, homomorphism, my bad. Okay, if it is an additive homomorphism, that is fx plus y is equal to fx plus fy, then we have to say that function fx will assume a linear form. So basically, functions of linear form will satisfy this particular equation. That's fairly easy to see, but let us see how it goes. So let n belongs to natural, then one understands that fn I can simply write as f1 plus 1 plus 1 1 1. So rather I would start with f2. What is f2? F2 is f1 plus f1, which is certainly 2 times f1. What would be f3 for that matter? It will be equals to f2 plus 1, which is simply 3 times f1, because it will be equal to 2 times f1 plus f1. Okay, so it is f2 plus f1. F2 is already, we know that is 2 times f1, and then f1, so 3 times f1. So in general, if I want to write fn, this will be f1 1 1 1 1 1 all added. So it is nothing but it is equal to n times f1. So for all natural number, one can say that fn will be equals to n times f1. This is the first thing that we can address. Okay, okay. Now, what about 0? So f0 can certainly be written as f0 plus f0, and which will be equals to 2 times f0. So 2 times f0 is equal to f0 implies f0 is equal to 0. So f0 is 0, that is certain. F0 is 0, that is certain. Now, similarly, what I can do, I can simply write m is equal to minus of n. So I know if n belongs to natural, then m will belong to integral integers, because see, m belongs to natural, so this will be negative integers only. So f m plus n will be equals to f0, and we know that f0 is 0. So what will be fm plus n? So it will be equals to fm plus fn. So fm plus fn is equal to 0, and I know that what is fm is equal to minus of fn, and is equal to minus of n times f1. And what is minus n? Minus n is simply m. So for every integer value also, I can say that fm is equal to m times f1. So if I want to take negative integer values, then also this is the true. Okay, so all positive integers and negative integers in general, for every integer I can write so. So for every integer, what should I say? For every integer I can write fi is equal to I times f1, where I belongs to integers. For integers, we've proven. We want to prove that fx is equals to lambda times f, f lambda times x. Here lambda is nothing but f1. So for all x we want to prove. So how would we go? We would try to do it with rational numbers. So let's say if r belongs to rational, and let's say r is equal to what? It is equal to m upon n. And what I'll do, I'll simply write f m as nothing but n times m upon n. Or simply put, I will write f of m upon n, m upon n, m upon n, dash dash dash, m upon n, all added, these all added n times. All these added n times. So this will give you what? This will give you fm is equal to f m upon n plus fm upon n plus f of m upon n dash 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 f of m upon n. So basically this is fm, which I can write it as m f1 n times f of m upon n. So similarly, if I want to write it as this way, I'll write f of m upon n is nothing but m upon n f1. Or in general, for every rational number r, I can write fr as simply r times f1. So this is true for all r belongs to Q. So what we have already established that fx is equal to x times f1, where x belongs to natural numbers, x belongs to integers, and even for x belongs to rational, we have proven the same, that fx is equal to x times f1. So now, what about any real number? Will it be true for every real number? Yes, indeed. See how. So let x belongs to r, and for every real number, there always exists a sequence of rational converging to that particular number x. For example, if x belongs to r, there always exists a sequence of rational converging to x. So Rn is any rational number which converges to x, x belongs to R. So for every real number, there always exists a sequence of rational converging to that particular number. So, and given that f is a continuous function, see, it is given already that f is a continuous function. So Frn must simply be equals to Frn must simply be equals to what? F of x. And what is, by the way, Frn? It is equals to Rn f1. So Rn f1 limit n tends to infinity, this will be equals to fx, and we know that as n tends to infinity, Rn converges towards x, so this will be x times f1 to fx. So clearly I can say that fx is equals to x times f1 for all x belongs to R. So in general, a linear function of the form fx is equal to lambda x satisfies this Cauchy's functional equation where lambda is equal to f1. So this is a very, very, very nice question for you people to understand. This serves as a very basic and the primary example to start with the functional equations. Okay, a few examples we are going to do today and a few uh, initiations, how to do questions in this particular, how to attack or how to approach these problems I'm going to teach you today itself. Okay, so this is very important, one must understand. Okay, now let us do a few more questions of this form, and let me first try to do another one. Mm, that was another functional equation. Okay, so let's try to do another question. So we want to determine all the continuous functions. What is our target? We want to determine all the continuous function. We want to determine all the continuous function which satisfy this. We want to determine all the continuous function defined from R to R such that f1 is greater than 0, and want to have f of x plus y is equals to fx into fy. So we want to determine all the continuous functions from R to R such that f1 is positive and f of x plus y is equal to fx into fy. This is something that we want to do. See how many continuous functions satisfies this kind of hypothesis. We want to find all those continuous functions which uh, satisfies this kind of hypothesis that it is continuous. One function is defined from R to R, f1 is written 0 and fx plus y is equal to fx times fy. So this is something we want to do. The first thing that we need to understand is that evidently it's quite clear from this particular initiation that f cannot be identically 0. So f cannot be identically 0 function, because see, if it is an identically 0 function, obviously this satisfies this. Basically, this satisfies this, because if you place 0, 0 here, if f is identically 0, then this will be 0. That's all fine. But the point is that f1 is always greater than 0. So we cannot have this kind of function. So evidently, I can write evidently f cannot be identically 0. So f cannot be identically 0. This is the first thing that one needs to understand. Secondly, see, if I take, because it is defined for all xy belongs to R, so this particular equation is true for all xy belongs to R. So what I can do, I can, instead of x, I can replace x by 2, and simply y also by x by 2, because if x is arbitrarily real, then x by 2 is arbitrarily real, then y can also be replaced by x by 2. This is completely arbitrarily real. X and y are both arbitrarily real. So basically, this proves that fx is nothing but it is equals to f square x over 2, x by 2. So certainly this is greater than 0. It implies that fx is fx will be in general non-negative function, or you can say fx is positive on R. Fx will be positive on R. This is certain. Fx cannot be identically 0. This we have already written. So fx is such a function which is positive on R. Okay, so we have to assume a function. Sorry, we know that fx as such function wise it is positive. So now let us define another function g of x, which is nothing but log of f of x. It is nothing but log of f of x. Since fx is positive on R, since fx is positive on R, one can think of such kind of function like f gx. One can think of this kind of function which is gx. Is that fine? I think this is quite easy to see. Since fx is positive on R, then one can understand that gx would be simply log of fx. This can be well defined. Okay, fx is a continuous function, and log x in general is a continuous function. So log x is a continuous function on 0, infinity. So clearly log fx is also a continuous function. Log fx is also a continuous function. Another thing to see. Okay. So log fx is a continuous function. So it implies that gx is a continuous function. Now, just think about this. So I know that if I want to write g of x plus y, g of x plus y will be equals to what? It will be equals to log of f of x plus y. And what is log of f of x plus y? It will be equals to log of fx into fy, and will be equals to log of fx plus log of fy. And what is log of fx? Log of fx is gx, log of fy is gy. So it implies that g of x plus y is equals to gx plus gy for all xy belongs to R. It implies that gx satisfies the Cauchy's functional equation. Gx satisfies Cauchy's functional equation. And if it satisfies the Cauchy's functional equation, gx must take the form of some linear function. And here lambda is equal to what? G1. And if gx is equal to lambda x, it implies that log of fx is equal to lambda x. And it implies that fx will be equals to what? E to the power of lambda x. And it implies e to the power lambda raised to power x. And certainly we can write it as b raised to power x, where b is greater than 0. So it implies that function fx will assume an exponential form. And it certainly will be always strictly greater than 0. Is that fine to you? So how many functions are, so function, what kind of functions will satisfy this kind of differential, this kind of functional equation? Only the exponential type of function. So all the continuous functions of the form b raised to power x, where b is nothing but f1 e raised to power lambda, and lambda simply g1. So such kind of functions can do. So basically, these are those continuous functions which will satisfy the above given functional equation. Few questions of another form can also be asked. Let's say in which you can use an inductive approach. So another questions that I want to really teach right now. A few more. Let me just take. So let me take another example. So the idea of these lectures is to quickly uh, give you these concepts. So let f be defined from R to R be continuous functions such that f of x plus y upon 2 is equal to 1 upon 2 fx plus fy, 1 upon 2 f of x plus f of y for all x5 belongs to R. So we want to show that linear function is the solution for such kind of functional equation. So linear solution of the form ax plus b will form the solution for such kind of functional equation. So let's see how it goes. So what I will do, I'll simply assume gx as simply f of x minus f of 0. So this is a kind of function I'm defining, and we know that f is continuous, so therefore gx will be continuous. We already know that half of fx plus fy is simply f of x plus y by 2, f of x plus y upon 2. And this I can simply write according to the given conditions. I will simply write it as f of half. I'll write here x plus y. This is 1 and plus 0. So this will be equals to half of f of x plus y plus half of f of 0. Okay, so according to the question, according to the given condition, I've done it. That f of x plus y upon 2 is half of fx plus fy. Simply this take it as z, so z plus 0. So f of half z plus 0 will be half fz plus half f0. This is it. So f of x plus y upon 2 is equal to half of fx plus y plus half of f0. Okay. Now from the question, from the assumption that we've done, we have assumed that gx is one function which is fx minus f0. I can write that g of x plus y will be equals to what? It will be equals to f of x plus y minus f0. So what I can write that g of x plus y is nothing, but it is equals to what I can write here. What is f of x plus y? F of x plus y is equals to what according to given question? Just let us see. Okay, so sorry. This is equals to half of fx plus fy. So from here, if I want to extract from here this equation, let's say give us equation number 1. So from equation number 1, it is clear that f of x plus y is nothing but it is equal to fx plus fy minus f0. So f of x plus y is nothing but it is equal to c2, take it to there. So this cancels out. So fx plus fy minus f0. So f of x plus y is simply fx plus fy minus f0 and again minus f0. So this is minus 2f0. This is your equation number 2. And what I can write simply that g of x plus y is nothing but it is equals to fx minus f0 and then plus fy minus f0. So g of x plus y is equals to what? This is gx and this is gy. So clearly from here it is clear that g of x plus y is nothing but it is equals to g of x plus g of y. So clearly g satisfies the Cauchy's functional equation. Gx satisfies the Cauchy's functional equation. So clearly if gx satisfies Cauchy's functional equation, it implies gx will be of the form of some constant times x. So this is equation number 3. And I already know that Gx is what? It is equal to Fx minus F0 is equal to Ax. Clearly Fx will be equals to what? It will be equals to Ax plus F0, and F0 I'm writing as B. So Fx will be of the form Ax plus B. So all these questions that I did today were inspired by Cauchy's functional equation. In the next lecture, we are going to continue with some more questions on Cauchy, on more questions of functional equations and continuity. Please let me know if you are following these, or if you need any kind of improvements in these. Please let me know in the comment section. Till then, take care. Bye bye.